Hello? Oh, why is that in my left ear? Hello? Is that better? Fix mic? Yeah, how do I fix that? Hello? Is that better? Yeah. Okay. Now you can't see me, so let me add. Video. Okay. Let's go like this. No. All right. Are we cooking? Can you see me? You can hear me? Chat's working. Voice is low. How about that? All right. I gotta turn. Okay, I promise I'll get better at this. Okay, so I got the YouTube chat here. Turn up the voice. Hello? Maybe I can do it here. Don't know how to. I think it's pretty good. Maybe I can speak up. How's that? Can I turn that off? Nope. All right, good. Okay, sorry about that. It takes a bit to get used to again. OBS has changed a lot. All right. I got the chat. I got the slides. I'll get Tiger VNC up for when we're ready for it. If someone's an audio expert, do you know how I can get rid of the delay coming back to my ears? What's down mixing? Noise suppression? Well, I mean, I guess I don't need my earphones. Do I? Let me just turn that off. Okay, that's way better. All right, simple fixes. All right, sorry about the delay. Just had a shower. That's not why I was late. I was trying to fix OBS. All right, week 1, lecture 2, and a bunch of admin stuff. Okay. It was great seeing you all yesterday for the lecture. And to have you all back today. Let's just get straight into it. So someone asked, should we open Tiger VNC? I would say yes, get it open. I think one of the benefits of an online lecture, at least for one of them, is that it's much easier for you to follow along. So for really more demo and programming heavy content, we're going to do it like this. Cool? All right. I'm monitoring the YouTube chat. Please keep it appropriate. We don't want to time people out. All right, so far we've just done some welcome and introductions and getting started. We wrote our first C program, which is obviously very exciting. Today, we are going to look at one of the fundamental building blocks of programming. This is one of the core concepts that's really, really important. when we are working with computers, basically, and it's about memory. So without the capability to store information, we can't do much. We can write programs like Hello World yesterday, but every time you run that program, it will do the same thing over and over, right? Let me show you that actually. In fact, I do need to figure one thing out. Which is, maybe this should go here, this should go here. Okay, so I can just oh, I've done that wrong. I see what I've done. Okay, hold on. Okay, I'll fix that later. All right. I guess I got to copy, duplicate this. Okay. Okay, I'll fix that later. That needs to be up here. All right. All right, so data and expressions. So a brief recap of the first program we wrote yesterday. Hello World. So, well, we have this, that's annoying. Int main void being the entry point of our program. This is just something we need to remember. When you see the function main, M-A-I-N, this signifies that what is contained in these two blocks is the entry point of the program. It's where the function and the program starts. We had this call to printf, hello world, which means the literal text inside of that string is going to get printed out to the terminal. And we exit the program here. Okay. In order to use the printf function, we must include standard.io.h, the standard input-output library. Okay, we compiled and ran this program. I am just going to do something here. Let me delete this. Remove. That should still be okay. I should do. Okay, that's better. All right, when we came over to our Tiger VNC here, and then I just need to put the webcam above that. All right, you remember that we had our, I put it in documents, I think, CD COMP1511. Swap this a bit. I type the ls command. I see I've got a directory called week1, so I cd to week 01. I type ls, and I had that hello world.c file that we created. Inside that hello world.c file, I had my program there. Can I just, there we go. That was the problem. I had my program here. And I compiled it with DCC hello world.c dash output to an executable named hello world. I ran the compiler and we get this executable output. I run hello world, and you see hello everyone, which was the string that I was printing, right? So this was the program that we all ran yesterday. Okay. What we're introducing today is a new topic, a core topic around data and variables in memory. And it's answering this question, how do computers store data? So let's have a really light look at theory. I'm just going to move the YouTube chat a little bit. Yes, thank you, Bree. If you're typing out a command in the terminal and you need, and you know there's only one or two things that are going to match that command or that term, that directory or file, hitting the tab key auto completes. It's really good. Okay. So yeah, how do we store information? So computers are electrical machines. They run on electricity. Typically, we either have voltage or no voltage running through a component. So if voltage is running through a circuit or a component of a circuit, we say that there is some charge there, or we have charge. So we have the Boolean value 1. When there's no electrical charge running through something, we have no charge, and we say we have 0 or nothing. And this is where the idea of computers being based on Boolean comes from. It's because of the voltage flowing through components. Now, I'm not an electrical engineer. Maybe they'll have more input to say there. We're talking at a very high level here. The point is, right, you know, a lot of people talk about computers run on binary 0 and 1, for example. And it's because these components they can remember a charge, right? They can remember if there was electricity flowing through the component or not. It can store it. And Boolean just means either on or off. So there's either charge flowing through a component or there's no charge flowing through a component. And we can really stack loads of those components next to each other so that we can store many Boolean values or zeros or ones, okay? Does that make sense so far? Just give me a thumbs up in the chat or something like that. So we either have voltage running through a little loop or we don't. Just think of it that way. And that allows us to store yes or no, 1 or 0, voltage or no voltage. Now, I don't know how slow the YouTube live chat delay is. So if you could say, yes, thank you, got it, Jake, continue, then I'll get a gauge for how long the delay is here. Okay, there's a thumbs up right now. So bit of a delay. Okay, so that alone gives us a single bit. A bit being a technical term here, it means one capability to remember a 0, 1. That can't do much. So that can help us remember literally yes or no. And that's it. So a single bit alone can't do much. But as someone in the chat has just pointed out, well, we could put lots of them together in a circuit, right? So what if we group these bits together? So I've got an activity for you. Can you see this okay? Maybe it's a bit zoomed out. I don't know if I can zoom in. Probably not. Can you see it? Looks good. Oh, fantastic. All right. So here's a little activity for you. You can just post it in the chat, I think. So what you're going to do here is, and just wait a second. So on the left, I've got a key. So this is letters of the alphabet. A, B, C, D, E, F, G, all the way through to Z. On the binary sequence, I have, now this is not the real binary sequence for an alphabetic character. Don't come at me. This is not valid ASCII if you happen to know what that is. But I've just made my own mapping to a binary sequence. So all I have here are 5 zeros and ones. Can you see that? 0, 0, 0, 0, 0, 0. Or is that 6? 1, 2. My eyesight's getting 1. Let me look at the ones. 1, 2, 3, 4, 5. Yeah, 5. I've got a sequence of 5 zeros or ones, 5 bits. And 5 is enough to give me all the way from A to Z, right? So what you can do is spell your name with the binary sequences. So for example, Jake, I'm going to do what? Write down 0, 1, I've lost J, 0, 0, 1, A is 0, 0, 0, 0, 0, K is 0, 1, 0, 1, 0, E is 0, 0, 1, 0, 0. Okay, so I've just spelt, my name in binary. I've looked up the characters of my name, mapped them over to a binary sequence, and spelt it out. So I hope, or maybe your name is also Jake, but you want to spell it in the binary sequence. So I'll give people a couple minutes to do that. How many people are in the chat, by the way? Participants? How do I look at that? Can't tell. Oh, great. Wow, 275. Nice. Cool. We have a question from someone. How does binary sequence relate to Morse code? I think it's really similar, right? Instead of binary sequences, they have dot and dashes, which is basically a different binary representation. And they've got a different mapping. So if you played a dot, as a 1 and a dash as a 0, then you could come up with your own binary. All right, a few people have put 1s and 0s. Some people have really long names, so that's tough. Okay, but why? What's useful here? What's important? Well, what you've done is you've taken a meaningful value, in this case, letters of the alphabet, and you've mapped them over to 0s and 1s. And so now the electrical components in a machine knows how to store 0s and 1s. That's what it's good at. And so if you can just store those 0s and 1s in memory of a computer, you've persisted meaningful data. Does that make sense? So you've done the work to map from real world data to binary data, and the computer can store that binary data. So I think that was my name. So this is a really important part though. 0s and 1s on their own don't mean anything to us, right? Like if I didn't give you the table earlier and I just gave you the sequence and I said, what does this represent? You wouldn't be able to tell me. So humans, we need to agree what a sequence of 0s and 1s means. Once we do that, we can actually do something useful with them. So, God, that's an outdated joke. So once I've got a sequence of 0s and 1s, how do I actually store them? Where do I put them? All right, in real code, like what do I do? And where do they go? So the answer is there's different types of places, and I know some of you will already know this, you're, engineering university students, but there's different types of places where I can store data on a modern computer. There's two key ones that I'm going to talk about. The first is RAM or memory. So when we talk about memory in, say, your comp courses, we're talking about those sticks of RAM that you might have put in a computer before or you hear about. This is mostly what we interact with and care about in this course. You also have persistent storage, so not so much a hard disk drive anymore, but a solid state disk, an SSD, that should be SSD. And there's many, many older variants. The big trade-off between RAM or memory and persistent data is speed. So RAM is much, much faster. Can someone throw in the chat the downside? There's always, with every benefit, there's a cost, right? So RAM is really, really fast, which is important when we're running programs. But what's the downside to, RAM-based memory over, for example, a hard disk drive? So RAM does store much less information. It is much more expensive. That's exactly right. It can't remember as much, but Shanae has it there and a bunch of other people, but Shanae got there first. It's volatile. And so what volatile means is that basically, so you plug your computer into the outlet or you have it running off a battery and it can remember those 0s and 1s, and then you unplug the power and the electricity stops flowing through the components and you lose all that data. It's gone. So it's volatile, meaning that once the electricity is stopped running through those components, it's gone. Whereas if you wrote data to a hard drive or a solid state disk, then it will stay there even after the power is removed, right? So this is temporary working memory. You know, it's just like your short-term memory and your long-term memory in your brain. Yeah, working memory, right? It's only while it's working that you remember it. Once you stop that activity, you lose it. But when we talk about writing programs, we're almost always talking about RAM. That's where we store things, because we don't really care what happens when a computer loses power. Can someone tell me why? If I've got a program like Hello World or something like that, I don't care if I lose. I don't really care if power's lost. The data is stored on the SSD. Yeah, that's if I store it on the SSD, maybe, but in that case, I don't. Yeah, exactly. Is it Niels? Is that how I say your name? If I've lost power, my program's not running anyway, and it's not doing anything. And also, like, if I run this program... Oh, you can't see this. If I run this program, Hello World, it's done now. It just finished. So because we had that return 0. So if the program's over and I lose power, I boot it back up, I can just run the program again. It's really not the end of the world. Oh, I didn't mean to do that. Now, we haven't spoken about data yet, so this is a little bit premature, but you get the idea. All right. Within memory, within RAM, okay. So I have a MacBook Pro. It's got, I can't remember how much data on it now. I think it's got 32 gigs of RAM, let's say. Within that 32 gigabyte grid, is the way I sort of think about it, we divide up our RAM into different components or different sections. There's 4 that I'm going to talk about now. I'm going to introduce you to them. I will say this is, I think, an accurate abstraction. So I will make some abstractions here just to make the content a bit easier to understand. But you know, like everything in life, there's always an asterisk, right? So there's always a little bit more depth that we could go into. You can't see me because my webcam is in the way. All right, down here we have the code section. Okay, the code section is the location in RAM reserved for the actual program executable that's running. So let me try and demonstrate this in an interesting way. I got to stop doing that. Oh my God, and I got to move this back over. All right. I'm going to open up that program we wrote yesterday, and I'm going to do something that we haven't sort of done yet. Basically, what all this does is, in fact, I can just do this. All this does, you should never write this, is it'll loop the program forever, so it won't end. That's all I want to do. So I just saved that file. I'm going to close code. I'm going to compile that again. Let's call it something out. Loop. Now I might get a warning here. No, I don't. Okay. I'm going to run loop. And you'll see how the program's not exiting? I'm not getting my prompt again. It's just stuck. It's running the loop forever. Yeah, and the answer is yes, you have to compile the code every time you make a change. I'm going to open a new tab, a new compiler, and I'm going to delete the loop executable. But over here, it's still running. If I look here, I'll prove it. There is no loop executable. It's gone. The program is still running though. So how is that possible? I remember the first time I learned that, I was like, what? That doesn't really make sense. Like the program's gone, So how is this running? Like if this was doing something, you would see it's doing it. It's not just doing nothing. So what's going on there? And if I hit Control-C in my terminal, I'll exit out that program. The reason it's only printed at once is because I told it print it once and then loop forever. So that's what happened here. The reason, got to stop doing that. The reason that program can continue to run is because when we run a program, the program gets copied into the code section of the memory of RAM. Does that make sense? Anyway, that was kind of just an aside to talk about that. Then we have a section of RAM called globals and statics, which is another cordoned off piece of memory that we're not going to talk about right now. Then we have something called the heap. This is very important, especially in the second half of the term. Yeah, my terminal looks a bit different than yours. Okay, so we have the heap. Then we have something really important. That's why I've tried to give it a bit of a gap to show it's a bit different. It's called the stack, and this is what we're focusing on in the first few weeks of the course. So the stack is just a piece of the RAM available to your computer that's associated with a program when it runs. And we'll have a look at why it's called the stack in a minute. All right, any questions while I get up something that I need to get up? We'll talk about the stack. It's kind of annoying. I definitely got to fix up my Okay. All right. So the way I like to think of it is that we have this basically big grid. Let me do it like this for now. We might have, for example, code over here that we don't really want to worry about for now. This could be the heap. And over here we could have, I don't know what this is. Oh, multicolor. Oh, we could have the stack. All right. We'll come back to that. Okay. So we can, what I wanted to really show you was that in our whiteboard, what we're really doing is, we can put zeros and ones in here, ideally, and we can read them and write them and refer to them later. Okay. All right. So conceptually, let's have a moment to pinpoint. Is it making sense conceptually? Do we get this idea that we've got information from the real world? Maybe it's text, maybe it's numbers, maybe it's images. We agree on the method for converting that into zeros and ones. Okay. We might have a table that we come up with, usually is what we do. Once I've got zeros and ones, I know that computers can store electrical charges in hardware, 1 or 0, voltage or no voltage. So if I can store those and get them back, then I can persist data and read to and write to it. Do we have any questions so far? Okay, we got a imposter from not from UNSW, but we welcome you here, Prime Rat King. A couple questions above reserved. Oh, okay, they're coming back. Okay, so stack is basically part of the RAM, which is allocated towards executing code. Let's break that down. Oh my God, I just opened you. So needy. The stack is part of the RAM, correct, which is allocated towards executing code. Yeah, that's right. So when you run a program, the operating system says, okay, a program's getting run. It will need some memory. I'm going to give it a bit of stack. It might need a bit of heap. It will manage the code component. You don't manage the code. So that red part is handled by the operating system, not by you. You get access to the heap and you sort of get access to the stack. But this, we're not ready to talk about this in that detail yet. The answer to your question, I would say, is that that's correct. We get an allocation of the stack. So the difference between code and stack is the code literally stores, like it stores, oh, you can't see, it stores like this code. It stores the machine code of your program that you compiled so that it can run it. Does that make sense? So the code is just getting copied over into the memory. The heap, we're not going to talk about now. We'll get there, in the future. But it's a chunk of memory that we can use, basically. I got to stop turning off the webcam. Didn't mean to do that. All right, turn off the whiteboard. Turn off Tiger VNC. All right, let's continue. Okay. So we need some mechanism in our source code for storing data. How do we do it? We use a concept called variables. This is a core concept. If you're taking notes, right, this is you want a section of your notes called variables, right? This is important. A variable is a label for a piece of memory. All right. So in our RAM, we can store zeros and ones. That's memory. In our code, what we do is we ask for a piece of memory and we give it a label. The label is so that we can refer to it in the future. It's a human readable term to locate the same piece of memory again. Does that make sense? They're called variables because the value in that labeled piece of memory is variable. It can change. I could store, the zeros and ones to store the name Jake. I could remove those and change the zeros and ones and rewrite them to store the name, Ben Mortimer. It's variable. What's inside that labeled block of memory is variable. This is important, okay? This is important. When I ask for a piece of memory from the operating system, I need to tell the operating system how much memory I would like. So, really simply, how many zeros and ones do I want to be able to store? How long is my name? How long could a name be? Because remember, I can change the names. So really the question is, what's the longest name that I might store? And that's how much bits I want to ask for. And then this one's also really important. Really important. Why is this important? Okay. When I ask for a piece of memory and I get back a labeled piece of memory, it can store a specific type of data. And this is kind of true and kind of not true. It's one of these things that's not technically true. Like I could store any type of data at any piece of memory, right? We are in control as programmers. But it's true in that you pretty much never want to do that. And the reason this is important is I want to go back to this table. On this table, we all agreed that the letter A was 5 zeros in a sequence. The letter U is 10100. This was what we agreed upon. This is our type, right? This would, you could call it the Rensselaer character type. 00111 might mean the letter H in the Rensselaer character type, but it might mean, in an integer, it means, 2, 4, 8. So it means the number 13. So the type of the data there changes how we read it and write it. So we want to keep track of what the type of data I said was at each piece of memory. So I think these concepts, while they're really important, will make more sense when it comes to actually implementing the code. Any questions so far? I'm going to continue because of the delay, and then I'll come back and answer it. Okay. For our purposes, so all these things are true, right? But some of them, the computer or the operating system or the programming language does them for us. So for our purposes, what we need to make a variable or to store some data is its type and its name. That's the label that I was talking about earlier. This is to make a variable, not to store data in it, not to read data in it yet, just to create a variable, a piece of memory. So let's look at some of these types. Let's look at some of these types. These are the really important base types of the C programming language that really make its way over to most programming languages that came later. These are the basic building blocks of how we store data in programs. These are the useful data types. So let's start with the integer, the int. This is the type in C. It's called int standing for integer, which lets us store a whole number. Right? The number 1, the number 4000, -5, 0. A whole number can be stored in an int. And if you think back to that table of the letters to specific integer bits, there is, well, in this case, you don't really have a mapping. It's much simpler, but we map a sequence of zeros and ones to a whole number, 5, -5, whatever it is. We don't really map integers because we can actually just do the calculation. So you don't need an actual mapping. All right, so ints are really, really fundamental. We have characters. That's what we were doing earlier when we did the mapping. But of course, the C language has its own character mapping, and it doesn't start at 0. It starts later on. We'll look at that a bit later. And you can store not just, capital letters like A through Z, but we can store lowercase variants, uppercase variants, punctuation marks, white space characters, new line characters, right? Any actual character that you might need to store. We have doubles, which is also a numerical data type, but this double store double precision floating point values. So for example, pi is 3.14159. That's a double floating point. There's other floating point data types, but double's basically the go-to now. And each data type has different memory requirements. Remember, we said when we create data, when we create a memory allocation, we need to know how big that memory allocation is. And the way it really works these days is that the language and the operating system, they agree what a sane, size allocation is for each type. So an integer in C, on my operating system, it could actually be different, but pretty much now this is the go-to, is 32 bits, right? So 32 zeros and ones in sequence, which is 4 bytes, if that makes more sense to you. So this isn't to say that, all integers can be represented in 32 bits. Of course, that's not true. Eventually we'll run out of space, but this is just like a big chunk of memory, decent enough to store pretty big integer numbers. Characters, we need less. We need much less because there's less characters, right? So there's a finite sequence of characters. Therefore, we only ask for 8 bits when we want to store a character. Doubles are called double because they're double the precision or double the size of, for example, integers. And we need 64 bits. The reason for it is, the way to think about doubles is you're storing 2 integers, the one before the floating point and the one after. So it makes sense that you sort of need double the size. And yeah, Limes has asked a good question. Is it important to remember these numbers? The answer is yes and no. I would say it's important. It's not important to spend time to memorize right now that an int is 32 bits. But you will need to know it, and you will eventually learn it. So I will say, yes, it's important to remember them. But I'm saying maybe you don't, like, there's other more important things to spend your time learning right today. Does that make sense? And yeah, sorry, one byte is 8 bits. So you're just multiplying by, 8 to get to 32. So a char is a character. A double is a double precision floating point over here. Character can store the letter A, the letter V, whatever. A double stores a floating point number. So these size limitations correlates to real limitation. So for integers, we can store numbers in this range. Minus 2,147,483,648 all the way to 2,147,483,647, right? This is the biggest integer you can store in 32 bits, right? That's if all the bits in 32 sequence of bits were flagged to 1 and you added them all up. Characters, we get about 256 different unique characters, and doubles are the same as integers because you have 32 bits on each side of the decimal point, 64 bits. But there's limitations to how precise a double floating point can be. Doubles are really difficult. Not difficult to use and learn, but programmers get into a lot of nasty trouble with floating point arithmetic because you have limited precision. Okay, so that's the type side of it. Do we have any questions on the type side of it? So Crunch has made a comment that these are useful to know when you get into more manual memory management, which is absolutely true. We'll do that later in the course. Most of the time the compiler handles it for you. Yeah, that's also true, especially in the stack. However, it's always useful to know what you're asking for from the operating system, right? So, but yeah, spot on. All right, I'm going to continue. Yes, thumbs up, and we will have a break in 10 minutes or so. Let's get through this sort of theory content. Yeah, decimals are really hard. Yeah. And in fact, I think at the end of this slide, I've got some images of things that have gone seriously wrong because of decimals or floating points. All right, I'm going to continue. Yes? I'm going to continue. Okay, so that was the type side. We also have the variable or the label side, the naming side. It's really important, right? Just because you can decide a label and come back to it doesn't mean it's not important. You should describe what it is you're trying to store in a variable, in a piece of memory, really accurately and economically. You can pretty much pick whatever you want to name a variable. In this course, in C, we have some rules for you. So we always use lowercase letters. For example, name is different to N, capital A, M, E. These would be different variables. I'm going to move that up here. But we always use lowercase in this course. And if we have multiple words, we separate them with an underscore. So this is snake case, not camel case. So naming variables is an art. COMP1511, I sometimes teach that course, goes into a lot more detail. This looks like a repeat of the previous slides, but with a bit more detail. So you can maybe cover this as notes. But let me see if there's anything here we haven't spoken about. Integers are whole numbers. Each bit gives us 2 possible values. This is the range. Character can store a single character like A wrapped in a single quote. Each character is associated with an integer. Yeah, I would just say to use these as notes. We can convert from characters to integers and back. That's right. A and A, right, uppercase and lowercase are different characters. Don't forget that. Characters are just ins under the hood. So that's always interesting to remember, but maybe not too important right now. Doubles are double-sized floating point numbers. Floating point meaning the floating point can be anywhere in the number. For example, 10.567 is different from 105.67. So the points are in different positions. It's called a double because it's usually 64 bits, which is double the size of an integer or a single floating point, which is a different data type. There was a question around the actual range of a double, which, I mean, I assumed I looked it up when I wrote the slide, but C 64-bit OS range of a double floating point. Okay, well, someone can read through this website and find the answer for me while I go on with the slides to fact check me. If there's something wrong with the slides, it's good to yell out and I'll fix them. Okay, what do we mean by floating point number? Like this is the example of why it's called a floating point. This is the same sequence of integers, right? 10567, 10567. But the point floats. Here it's after the second decimal, and here it's after the third. That's why it's called floating. It can float in the sequence to give us the number that we want. The cool thing is, like, when you're storing a floating point like 105.67 or 10.567, you don't really have to care about these things. It is all handled by the operating system, by the compiler. But it's just why it's called the floating point. So I think that answers your question, hopefully. There was another question I saw. What is meant by floating point? Why do the specific limits exist? Okay. The limits exist because we have to, like, when I'm storing an integer, I've only got a limited amount of memory, right, that I can store. So, like, because there's only limited, like, even in a modern MacBook, I've got 32 gigs of memory, 64 gigs, and that has to store all the memory for all the programs running on every machine. So memory is limited, especially when the C language was designed in the 50s and 60s. C language was really limited. So we can't just say that, hey, you get, 1,000 bits to store an integer. You'd be able to store one integer and that's it. So we had to give a reasonable limit to our data types. And by giving it a limit of 32 bits, that translates to this real limit, okay, of what an integer can be stored as. And the limits are different for each data type because there's more involved to store different things. Okay. All right. That was a little, let's call it light theory. Let's get real. Okay, how do we actually write code to store variables? It's really simple, actually, in C. You give the type, you specify the type, you specify the name of your variable, and that's it, actually. That will create a variable. So here's 3 examples. In this example, I'm using that int keyword, integer, to store a variable called age. Here I'm using that car or character keyword to store a variable called first initial. Right? Here I'm using the double type keyword to ask the operating system for enough memory to store a double, and I'm calling it pi. So let's actually do this. Still in week 1, let's create a new programming file to write a new program in. So I'm going to, you can do two things. We can touch the file like we did yesterday, or we can do code space, let's call it variables.c. If you just do code variables.c, it will create the file and open it up in Visual Studio Code for you, which is quite nice. And I get that blank file and I just hit save. Don't forget to go, file, save, or Control S. All right, let's write the shell of our program. Hash include standard.io.h. I'm going to go a bit faster. You can catch up. I'm going to do int main void, right? This is exactly what we did yesterday. And here I have the shell of a C program, or the boilerplate of a C program. Here I'm going to say, we can do a printf just to make sure everything's working. My variables program. If you saw in the slides, or if you ever see this \n, what that does is say print a new line character. So it puts an empty line underneath the statement. And this is a comment, which I think we spoke about yesterday. Now I can't remember, but comments are just non-executed lines of code that document things for us. All right, this is just a boilerplate. We're not doing anything with variables here. We just want to make sure that our program runs as we expected. So, well, let me ask you guys, I wrote this program. I have variables.c. What do I need to do now in order to run this program? We have to compile it. Very good. We use the DCC compiler. We're compiling variables.c, outputting it to a program called variables. Okay, no error. Let's run that program. And we get my variables program, and see, we have that new line getting printed out. So we're just set up for success. Very nice. What does void mean? Void means nothing. We'll talk about it more in the future. I'm going to skip over it. Yeah. Oh, did you hear that? Oh, probably not nice. Sorry about that. Okay, that was my neck cracking. All right. Every single time I run this program, it does the same thing. Does this program request any memory from the operating system? Right now. While you put in your answers, standard.io.h is the import or the include statement, just so that we can use printf. Printf lives inside of standard.io.h. So some people are saying yes. Can we do a poll? How do I do a poll? A poll. Does this program request any memory? Okay, while you fill that poll out, I'm going to fill my water bottle. Whatever, you can see me float away. Okay. Do you see the poll? It should be on YouTube. I got some answers here. Okay. Oh, that's a really good question. So are we declaring an integer variable on line 3 int main, or does the void make it do something different? That's a really good question. This isn't a variable declaration, but you're absolutely right that it looks like one. And you're also right that this changes it. This is actually something called a function declaration, which we just haven't covered yet. But yeah, it looks similar. You're close, but not quite. Not quite the same. Okay, does this program request any memory? I can't see where it's requesting memory. The answer is no. There's no memory declaration here, so it's not requesting any memory on the stack. There will be memory associated with the creation of this program, but my question was, does this program request any memory? And the answer is no. Okay? There's no... we request memory by one of two ways. At this point, it's through variable declarations, and there is not a variable declaration in this program. Okay. When I save this file, Limes, when I do file save, when I do file save, it's saving it to my hard drive, to my solid state disk. No, not to RAM. We're not using scanf here, right? So scanf is not something we've covered yet, so there's no memory associated with this. Okay? Hopefully that clears it up for you. But we want to change that. Let's request some memory. Okay? So the way we do that, remember, is type space name. So let's store a number. We're going to store an integer, and I'm going to call it, I don't know. Why is this so hard? Coming up with examples is the hardest part. We can do, drinking age. Okay, so we have a variable called drinking age, and it's an integer. When I run this program now, so I go back to my terminal, I hit up on the keyboard, I recompile it. Now, I do get a warning here. We can ignore it for now. It's basically saying you've created a variable, but it's not doing anything. So if you've done exactly what I did, you will see this. It's normal. It's just a warning, not an error. We'll talk more about warnings and errors soon. I run that program. I see my variables program, and it's the exact same thing happens because we've just asked for... This asks the OS for some memory, but does nothing with it. But this is still really cool because it means in our program, I've requested, some memory. So how many bits of memory has this program requested when it's run? Exactly, 32 bits, because an integer is 32 bits. Yeah, excellent, really good. Very, very good. Well done. Great. Okay, do we want to break now, or do you want to continue? Oh, we're running a bit behind. Sort of. Okay, let's have a break. Then we're going to come back and we're going to go through this content a bit faster. All right, quick break. Go. Okay. I'm back. Did you miss me? I gotta fix up this whole thing. Hello? 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 Okay. Are we ready to accelerate? Good to be back. All right. How long was I gone? Was that 5 minutes? Should I wait a bit longer? We don't really have the time. I'm going to get into it. Okay. In our program, I missed you all too. We created some variables, but we didn't do anything with it. How do we actually store data in those variables and read data from those variables? That wasn't 5 minutes. Too bad. Life's not fair. So here on the slides, you'll see, here we go. We're declaring an integer here, int my age, whatever you want to call it. How do I assign a value to it? Well, we use the assignment operator and we put the value on the right-hand side. So that variable that we created earlier, my age, has that label my age. When I use that label, I'm referring back to the data created on this line. And the assignment lets us assign the value 25, assign it to the thing on the left. And because it's a variable, I can change that. So here I'm updating it to no longer store 25, but to storing 28. So on my program, I can do, for example, drinking age is equal to 18 in Australia. Oh no, Americans. So the drinking age becomes 21. So when this program ends, there will be a piece of memory in the stack with the integer representation of the integer 21. Okay? The label is just for us on the programming side. It's not stored in the stack, for example. We'll talk more about what it actually stores in the future. Okay? So we can store some data. So what? I mean, like when I run this program, let's compile it again. Let's run it. It does exactly what it was doing before. I'm not getting anything interesting coming out of this. So what? How do we actually do stuff with it? Well, we can print, of course, what's in those variables. And we use that same printf function that we've been using. And we can use it in such a way that it prints the value of a variable. So printf requires what's called a format string. So a single string gets printed from printf. In this example, I am blank years. And these blank spots are format positions for data types or for variables. So in this example on the slide, I'll make myself a bit smaller. On this example on the slide, I have an integer variable called my age, and I've assigned it the value 13. We've done that on the same line. Yeah? That's something that you can do. Here I say, well, I want to printf the following format string. I am %d. Okay, what does that mean? We'll talk about it. Years, exclamation mark, comma. Right, this is all going to printf my age. So my age is going to get substituted into the first placeholder position. So this %d is a placeholder position. And we use %d for a decimal integer. So that means an integer will go into this %d. And the format specifier must match the data type passed. So unfortunately, one of the sort of annoying things about C is that we have to remember these format specifiers. So for characters, letters A through Z, whatever, we use %C. C stands for character. That's pretty easy to remember. %D is for decimal integer. It's a bit annoying because decimal feels like it should be double because the double is called double, but it's just not. We have %lf for long floating point. This one's the double. I didn't invent these, guys. Don't come at me. So it needs to know the type of variable that it's going to be printing and in what order, because you can have multiple variables. So in this example, the diameter is an integer assigned the value of 5. Pi is a double assigned the value of 3.141. And I print out a single string here, the diameter of blank. Pi is blank. So the diameter of diameter, which is 5, so the diameter is 5. Pi is 3.141. Does this make sense? Let's look at it. All right. So I've got my drinking age here. It's set to 18. Then I set it to 21. Let's also create int my age. I wish I was 25. I'm not, but I'm just going to put it here for now. I don't really wish I was 25. I take that back. All right. So let's print out my age and my drinking age. So I go printf. I always give it a string. Printf always prints out a single format string. And I might say my age is... Now, what would I put here? I can't put my age because it's going to just think that it's part of that string. It's going to print out my age is, literally my underscore age. So I need to say, well, I want to print this variable. So I do %d. And then after I do comma, what is the decimal integer that I want to print? In this case, it's my age. So my age is %d. My age is going to fill in that gap. We go over here. Let's clear the terminal. Let's compile it again. Let's run it. We ignore that warning. And we get my variables program. My age is 25. Look at that. We stored a piece of we stored a value in a piece of memory, and we were able to retrieve it and print it. That's really cool. How do we do multiple? Of course, we said my age is this, and the drinking age is, it's going to be also %d. I need to do comma, and I just put in that placeholder drinking age. Again, I come over here, I clear the terminal, I run the compiler, I run the program, and we see, look at this, my age is 25 and the drinking age is 21. So Shanae has asked, why is there a %? The reason we have percents here is because if we didn't, it would just look like the letter D. Right? We need a way to signify that that is in fact a placeholder. Oops. What if you want to print multiple variables of the same type? I mean, that's what this is doing. My age and drinking age are both integers. So maybe I'm not getting your question, Lachlan. You might need to re-ask it. Oh, the percentage in the output is because there's no new line at the end. So if there's no new line, this is just telling me that there is no new line at the end of my output. So now it's gone because I put that new line character here. Wow, good job. You can use multiple of the same placeholder variables and match in order. Yeah, absolutely right. Thank you, John. Any questions? All right, I'm going to continue. Can I continue? Thumbs up. I've got let's do that at the end of the lecture, but remind me to come back to that. Is there any no, it's specific to D. It has to be D because D is a decimal integer or an integer. So because this is an integer, because I'm printing an integer, it needs to be %d. All right. Yeah, remind me to do the feedback form at the end of the lecture, please, admins. All right. So that was writing data and reading them. Oh yeah, all right. Okay, yeah, this is a busy lecture. I always forget how dense this lecture is. Don't worry about the feedback form. I'll talk about it at the end. All right. So at the moment, we were printing variables that we assigned to, values that we assigned to a variable straight into printf. But we can also read variables from the user. So we can go the other way. Does that make sense? So that's the scanf function, scanf. So printf, print a format string to the terminal, scanf, scan a format string from the terminal, from the user. So this lets us read data from the user. We use the same ideas as printf. We use format specifiers the same as printf, but we need this ampersand symbol, and I'll show you where that goes. And for now, we're not going to really talk about it. Okay. Yeah, in this case, decimal doesn't mean decimal point. It means a base 10 integer. Decimal, that's what it means. 10. Not decimal points. That's floating points. Okay, anyway. All right. How do we do some scanning? So here's basically the smallest program. Well, there's no main function here, but I just skipped that for the slide. But here's a really small program that reads a value from the terminal, from the user, and stores it somewhere. First thing we need is somewhere to store it. All right. So if we're reading an integer, we need to create an integer. In this case, I've called it input. Then we ask the user to prompt. So please enter your age. Like the user needs to know what to do. It's not mandatory, but otherwise it's just the user's not going to see anything. And this is the really important line. And you can see it's not crazy different from a printf. So we say %d, we're scanning in a decimal integer, right? An integer. So that has to match. And the input goes after the comma, just like printf. However, for scanning, you need to put an ampersand before that input. You can just think of it as like opening a hole to go into that variable. It's like into input. We'll talk more about it and actually explain it in about week 6 or 7 or something like that. Hopefully not everyone. You can't hear all that. Someone's doing gardening or something. All right, so let's show this in code. So the drinking age is going to be 21. You know, that's all fine. But I don't know how old my user's age is, right? I don't know that it's going to be 25. So let's read it in from the terminal. Let's not guess. Let's not assign it in code. That's really boring. It's very static. So how do we scan the user's age and assign it to the variable my age? Well, the first thing we might want to do is do a printf, enter your age. Okay, so now the user will know, oh, it's asking me for my age, and we need that really important line, that scanf line. Scanf. Scanf is a function call, just like printf. What's the first thing that the scanf call needs? It's that format string. What are we scanning from the user? We're scanning an integer. We're scanning the age. So an integer needs the specifier %d. Okay? Where are we going to store that integer? We're going to store it in the variable called my age. I can't just write my age there. That won't work. I need to put an ampersand there for now. You just have to trust me that you need it. We will talk more about what that actually means in the future. So these 3 lines stores an integer, or like declares an integer, 32 bits from the OS, asks the user for their age, assigns it to my_age. Then later, if this all works well, we'll print it down here. So let's compile it and see if this works. Clear the terminal. I'm going to compile the program. I have an error. This is a good time to talk about errors. I've made a mistake in my code, and this time I've genuinely made a mistake. Let's read it. How do you read an error? Well, it's telling me, the compiler is telling me what it thinks I got wrong, or what it knows about what went wrong. Now, the compiler can only tell me its best efforts. It doesn't know what I was trying to do or necessarily what I got wrong. But in this example, it's saying on line 19, there was an error. It expected a semicolon after an expression. So there's this scanf line that I wrote, and then there's nothing there. And if we look, after an expression, we should have a semicolon. But I forgot to just hit the key on my scanf. And so the compiler thought that this is most likely an error that I've made, and it's correct. I will point out that we have this idea here, DCC help. So some errors, like this was a really easy error to fix. Some errors are not as easy to fix. And one of the things people started doing is going to ChatGPT to get help, but ChatGPT often gives people not necessarily incorrect information, but answers that we wouldn't apply to the scope of this course. So DCC Help is our own generative AI tool that you can use to get help about what you've done wrong with a relevant to the course explanation. And remember, all generative AI can be wrong. And also remember that when you come to your exam, you won't have access to DCC Help. So it really is just to help you when you're really stuck on something, but you shouldn't rely on it. So you get a nice description here. Every statement typically needs to end with a semicolon in your code. The scanf line is missing the semicolon at the end. The compiler is expecting to find the semicolon. So to resolve this, we need to make sure that every statement ends with a semicolon. Like this was a really simple example, so it wasn't too bad. So I added the semicolon, I saved the file, I clear this, and then I can compile it again. So I fixed my error, I recompiled, and look at that, I get my variables program. Okay, this is different now. So it says, my variables program, enter your age. It's paused, it's waiting. If I stepped away from the computer, and I come back, this will stay there basically forever until the operating system either quits my program or the computer runs out of power. The scanf call halts the program's execution until it completes, because it's waiting for me to enter something into the terminal. And I can enter my age. Do you guys know how old I am? Do you want to know? I can put my real age. So I'm 30. So I type in 30 and I hit enter. And then look at that. It continues. You know, my age is 30 and the drinking age is 21. This is really cool. We read a value from the user. We turned the number 3 and the number 0 into zeros and ones. And then we assigned that to the stack in RAM. And then we reread it from the RAM, even though it just happened right below it. And it might not look like it. We read that from RAM and then presented it back through printf. So printf is doing that difficult job of converting the zeros and ones and things into the actual text, the ASCII that we want to read in the terminal. Is this cool? Do we have any questions? That's a good question. What if I enter something that's not an integer? And the answer is we don't know. Probably some sort of error. So there's a whole stream of programming around error handling. We're not going to talk about it now. But there's things you can do to make sure that the user entered a character, integer character. But for now, we just want the user to make sure they enter in the right thing. I opened a new code to run the scan program and noticed that the variable's copied over. Am I doing something wrong? I don't know exactly what you did. It sounds like you opened maybe the same file again. Yeah. So how does it distinguish between the different %Ds? Okay, that's a really good question. I think you're talking about this line. I like this question. We have 2 %Ds, so 2 slots for a decimal integer. And it's really simple. It's just the first one goes to the first one, and the second one goes to the second one. It's that simple. Cool? All right, how are we feeling? Thumbs up in the chat if you're following. Can you tell me, am I going too slow? Am I going too fast? Can I get a bit of feedback from you guys? Thumbs up. Good. You can say faster, slower, goated. Yeah, goated. That's always nice for the ego. W's in chat, yeah. Maybe I will become a Twitch streamer. We did have a term, I will say, while you're doing that. When I first started teaching at UNSW, it was during COVID. And so obviously everything was online. And I don't know what happened. I guess, lots of people had this during COVID where like everyone was at home just watching stuff. So we got like thousands of live viewers on the YouTube, like on the lecture streams. And there were all these people, they were like spamming inappropriate things. And like the moderators had a breakdown because they couldn't keep up. We became like real streamers. And then we had to end it all. I mean, I don't get any money from it, but it was pretty fun. All right, everyone's pretty happy with the pace. That's really good. Let's keep going. No rest for the wicked. I do fan meet and greets. Yeah, you can come to the Monday lecture. So there's your fan meet and greet. Yeah, it was a bit of a nightmare. Okay, a few more details about scanf. You can't see my slides because I need to do this. I need to make that better. No, please don't spam, John. That was an invitation. Brianna will be sad. Okay. A bit more information. Scanning an integer ignores white space. That's sort of an important point. So if I go like space 3, enter, then the 3 will be assigned. That's good to know. Scanning a character, however, does not, because a space character is a valid white space. So what you do there is you put a space before the %C, and that tells scanf to ignore any leading white spaces and just get the first non-white space character. I've missed Liam's question. I must have missed it, but John's got it. Okay, that's scanning and writing. Yeah, that's scanning and printing. Let's talk about constants. Constants are like variables. They're stored data-ish, sort of. I'll explain what I mean by that. But they're values that don't change in the life of the program. And the reason they're useful is because they have less of a performance implication on your program. So if you have some types of data are better suited to be constants because they're not variable, they won't change. And so you should define them in the way that you're seeing on the screen. So a really good example is pi, right? Hash define pi to be 3.1415 because pi never changes. As long as you have enough precision, you don't need to store it as an integer because that means you have to ask the operating system for memory, put the memory in there, blah, 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 blah. If I just do hash define pi as 3.1415, I'm getting a value of a label pi for this constant value. And so the cool thing about constants in C, like this is the reason they're really cool, is because there is actually not a memory allocation happening here. So I'll let that sink in for a second. We're not asking the operating system to store that. You know that because there's no data type. It doesn't say pi is a double or anything like that. It's just like a mapping in the code. We need a hash. That's a good question. We need a hash. So this is a macro level activity. Hash define, hash include. These happen in the preprocessor. They're not actually part of the runtime of the program. We'll talk more about it in the future. Yeah, okay, using variables, this is cool. So once I've got an integer value, I might want to do things to it. So I can add integers, add doubles, subtract, multiply, divide. These happen in the normal mathematical order that you're used to, so BODMAS or whatever, and brackets force precedence. Do you call it BODMAS these days? What do you call it? you know, brackets, division, multiplication, assessment, addition, subtraction, PEMDAS, whatever. I called it BODMAS when I was in school. Anyway, so here's an example. So my age is 28. I was probably 28 when I wrote this slide, so that's funny. The current year is 2023. I take the year and I make a new variable called year born, and I assign it the expression, the current year, 2023, minus 28. And that will get, you know, whatever year it is that I was born in. And then I can print that out. So that's a really basic introduction to arithmetic. Of course, we'll talk a lot more about it in the future. Characters. We haven't really looked at characters. Let's look at some characters before we go on with the slide. In fact, I might actually just make a new file. I'm going to save it. I'm going to call it cars.c. And then I'm going to say, you know, hash include standard.io.h. int main, give it void, return 0. Okay. Same thing as before. Now, instead of an integer, I want to, not a chat, I want to store a character, and I want to call the character initial. Okay. So I could say initial is equal to the character J, capital J. So characters need single quotes to wrap them. Okay, they need single quotes. Strings need double quotes. So that won't work. This is not a character. This is a string. We want single quotes. Then I can, you know, do what I was doing before. Printf %c, right? Because this is a character now that I'm printing, and I can print initial. And if I put a new line at the end of it, maybe, and I go back to my terminal and I go DCC, what did I call this? Cars.c, output to cars. And I don't have an error, which is good. And I run cars. I should just see the letter J printed. Okay? And the interesting things about characters are that they are literally just integers in C. So C is still around today because it's very, very performant. And one of the ways that it was so performant is because they didn't do very much in the language. So they didn't add a whole bunch of stuff for characters. They just said that if you use the type character car, you get an integer, but we'll treat it as a character. So what that means you can do is cool things like this, sometimes cool. So here I'm creating a new character called letter, and I'm assigning it the character B, right? But like I said, character is just an int. So I can actually just add one to character, and it will become the character C, because there's like a mapping. Someone wanted to see the code again. If you don't believe me, I can say print initial plus 1. That's going to say whatever initial was, add 1 to it, and print whatever that is. If I recompile it and run it, I get K. It added 1 to it. Should we use an empty character when defining characters that have no current assignment? Yeah, absolutely. That's what I've done here. Well, I've not used an empty character. I just haven't assigned it yet, and then I assign it later. Because this might come from a scanf or something like this. Okay. I'll tell you one thing. So that mapping, from characters to integers is what's called the ASCII lookup. So if you type ASCII into the terminal, you'll see that mapping. So 0 is something called the null character, which we don't care about. But like the letter A, capital, is the decimal 65. The letter J was 74. So when we added 1 to J, what we were really doing is adding 1 to 74. When we printed 75 out, because 74 plus 1 is 75, we get K. Someone asked, well, what about Z? But Z is not the final ASCII character. So Z is here is 90. So if you added 1 to 90, you would see open square brace. A better question would be what happened if you added 1 to 127. But I'll leave that for the reader. So this is the ASCII standard that we all know and love. Okay, let's go back to the slides. Don't forget your limits. I mean, this is kind of what we're talking about. If you add two large integers, let's say you've got the integer 2 billion, that's within the integer range. You have another integer, 1 billion, that's also within the integer range. You add them together, and then you store that in an integer. That's 3 billion. That's outside of the range. What you get is an overflow. You roll around to the minimum value and possibly end up with random negative values that are difficult to predict. This is not out of the question. So these types of errors have killed people, many people in the past, and lost millions and millions and millions of dollars. So here we go. Why is the number 2147483647 important? Because as we mentioned earlier, it's the upper limit for an integer. And if you accidentally go over that number, here's an article, I don't know, for some reason, going on for forever talking about it. But there's many, many, many examples like that. Yeah, it goes boom. Not good. Here's some more examples that are fun. The Boeing 787 actually has in the manual, in the handbook, that it has to be rebooted every 248 days because there's basically, I think it's just the counter for how long the plane's been running for just counts up and eventually just overflows over its 2 billion seconds. I think that's something like that. Because what's 2 billion seconds in days? Can someone tell me? If it's about 2.17, whatever it is, if it's about 249 days, then that's what it is. So what they say is instead of fixing the bug or whatever it was, they just put in the manual, make sure you reboot the plane every so often. Which is not actually a bad idea, by the way, because memory leaks and other things can be difficult. And there's a few other examples here that you can view in the chat. Gangnam Style breaking the view counter for YouTube because it went over, a couple of billion for the first time. They didn't expect that. There's ways to fix these problems, by the way. We use custom data types or new data types that are bigger, but you've got to do that work. You don't just get it for free. So some doubles. I mean, unleaded, that's why would they not just store how many times it reached the max of that counter and then reset it? I mean, that is sort of the type of optimizations you would do for something that could get too big. They're just not doing it. And I guess writing airplane code is quite difficult and you would need a lot of authorization and testing. And so it's easier just to say to reboot it, potentially. I'm sure it's changed now. That's probably outdated. Okay, well, maybe it was probably milliseconds. Yeah, it's probably you wouldn't really count something in seconds. It's probably milliseconds or something like that. I don't know. Okay, doubles. Doubles cause even more problems than integers. If you thought integers were bad, doubles are way worse. There's so many problems with them, but they're pretty good. So, for example, 1/3 is an unreal number, right? Is that right? I'm not the best mathematician, but you can't actually represent something with infinite precision in a double, right? It's just not possible. A double has limits as to how many decimal places you can have. Some mathematical, values don't have that capability to just have a fixed precision. So we do tricks. I meant irrational. Thank you. I need to go back to school, clearly. So we do tricks. So for example, if we divide 1 by 3, we get an approximation of a third, but it's never actually exactly correct. However, most of the time, the types of things we do, we don't need infinite accuracy, right? So it's pretty, what's the thing? So if you're sending a spaceship to the moon, you can do pi with like 5 or 6 places of precision. You don't need a million, right? It's like surprisingly low. I kind of made that number up. Maybe someone can find what I was referring to. But these little approximation effects can cause serious problems. So watch out for them. Okay. Okay, this is more important for you guys, I think. C thinks in data types. So pay attention here because it'll cause you problems. If I have 2 doubles and I do something to them, what will the result be? In fact, we can write some code to do this. So while you do that, I'm going to do, whoops. Oh my God. So if I multiply 2 doubles together, I'm not getting an answer. What would that result make sense to be? Ricardo says a double, someone says a quadruple. So maybe the answer is that it's not quite clear. So the answer is a double, right? So if I've got 1.0 and I add 1.0 to it, I'll get 2.0. That's another double. And that's what we would expect both mathematically and just logically. But the problem is sometimes how we store these values influences how they're stored. Okay. So let me show you what I'm talking about. Here's a little program I wrote. Double A 2.0, double B 3.0. Int result. Result is an integer. If I say A plus B, we would expect to get 5.0 returned, right? I assign that to result and I print it. I go to my terminal. I clear the ASCII. I compile. The program. I run it. And I just get 5. I don't get 5.0. Maybe to make this a bit better, I'll do, 2.5 and 3.2. And I still get 5. Like, what the hell is going on? Now, this could kill people, right? Like, if I was, like, writing trajectory code and this needs to go in a certain angle, and it's just rounding to a 5 for some reason, like, what's going on here? This will cause people problems. And so you need to remember it. And actually, in this case, what it does is, so if you're paying attention here, this should be 5.7, right? But prints 5. What the hell, Jake? That was a typo. All it does, and the problem here is, if you haven't spotted it, double plus a double, but we're storing it in an integer. So result can only store a whole number. So actually, this gets cut off. So it doesn't round, actually. It just gets removed. Because that precision doesn't map over to the integer data type. Yeah, what the hell? That's what everyone says these days, right? Okay. So there's a few ways around that problem. Oh, that's where my slides end. Nice. And I'll show you those in code, I suppose, then. They should patch that out. Well, it's been in here since, the 50s or 60s. So yeah, the answer is that this should have been a double. It was an inappropriate data type, okay? Which means this should be... Oh, no, whoops. I'm in the wrong program. This should be a double. Now result can store 5.7. This needs to become a floating point, long floating point. I go back to my terminal. I recompile it. And I'll get 5.70000. And we're happy. Are they still not allowed to change language? You can't change this behavior now. It's way too far gone because millions of programs have been written requiring now this behavior. Even though you might argue that maybe an error should have been thrown or something like that, but you can't change behavior of a language like C. It's why more modern languages like TypeScript, Go, Python, they version their languages much more in small increments so that they can, if they really want to, make breaking changes. But breaking changes in a programming language is really rough. No one likes it, so you don't want to do it. So yeah, it just cuts off the decimal point onwards. How does it know how many zeros to do after the decimal point? You can actually control it. I forget how to do that now. I think you do it here, right? Someone needs to tell me. You do it in the specifier. Precision C. I'm just Googling it. Okay, thank you. So you do 0.2, for example. We'll give you 2 spots. Yeah, that's right. So it means after the decimal point, you get 2 spots. Thank you. Recompile it. And you get 5.70. And I think the way that works is you can do, for example, 2. You can specify the number beforehand. Is that right? In this case, I think maybe if that was like something like this, maybe it might actually do something. Maybe it just doesn't actually do something. Never mind. Guess that doesn't do what I thought it did. So let's just get rid of it. But yeah, you can just, but it's not, so the key to remember with this is that it's not changing the variable, right? So the best way to present this is if I just print it again, but oops, it's not going to copy. Oh no, what's happened? Oop. Right. I'm not actually manipulating the data I've got stored. I'm just changing how it's being printed. So it's just something for the printing formatter. Cool. All right. Well, that was a dense lecture. That was 56 slides. Well done, everyone, for getting through it. Now, there's a few important things I need to talk about. And while I do that, I need to get the feedback form. Okay. So I got to test this actually myself. To make sure it's the right one. Let's see. Okay, that's the right one. Now, for all you UCID imposters, the form, so I do a lecture form, feedback form at the end of every lecture, at the beginning of every lecture. It does check that you're a UNSW student for the exact reason that we have imposters in the chat, but I don't record anything about you. So it is purely anonymous, but I just need to make sure that everyone actually is a student that's doing the form. I don't actually mind if people wait, people watch the lectures online, as long as they're polite. Silly you said. So while I leave this up, there was 2 things I want to talk about. One is that next... Do I have a link we can share? Good idea. Good idea indeed. Okay, I need to do collect responses, copy the link. That's the link. All right, so there's 2 things I needed to say, 1 or 2 things. One, next Monday is the King's birthday. Apparently that matters to us. So it's a public holiday. No lecture. Yes? You can go to the campus on Monday, but I'm not going to be there. In fact, I will be actually in London, but not for the King's birthday. That's a funny coincidence. I just realized. So there's no lecture on Monday. because I'm so, nothing gets me more impassioned for life than teaching. I will record a video and put it on the lecture, on the playlist for Monday's lecture. So whatever I was going to talk about on Monday, we don't really have the time to just skip it and catch up. So on Monday, by Monday, before Monday, there will be a video, and we'll send an announcement out about it so you can watch the video. I'm not meeting with random students. You could be a UCIT student, right? Like I can't do that. I can't be seen. Okay, if you got to go. So just remember, no lecture on Monday. Keep an eye out, therefore, on your emails for announcements, because we will tell you what that makeup video is. On Tuesday, there will be a lecture, but Sasha, who taught the course in T1, will be taking it again because I'll be in London. And then I'm back afterwards. I'm back for the next week. So there's only a live lecture on Tuesday next week. Bree, John, is there anything I'm missing? It is 12:55. That is the formal end time of the lecture. Please fill the feedback form. It's really important to me to get feedback from you. Please be polite when you do that, of course. Go to your classes this week. Oh, yeah. Thank you. If you have a Tute Lab on Monday, it won't be running. So there'll be makeup classes. So pay attention to the information about that. If your Tute Lab is on any other day, you're fine. It doesn't affect you. There's always a public holiday in a term. It affects some people. We know how to deal with it. Well, thank you, Cyan. That's very kind. Plug the 1511 cheat sheet. Good idea. I'll even show you how to find it. So you go to the course website, you go down, is it to the bottom, and you go cheat sheet. I'll give you the link. And there's a nice cheat sheet around how to get around the terminal, some of the stuff we've spoken about, copying, moving, making directories, concatenating files. Yeah. Cool. All right. Well, I promise I'll improve my streaming setup. It's been a couple of years since I've actually had to use it. Thank you all for coming. I will see you in a couple of weeks. You'll see me in a video on Monday. Bye.